A resistor is a passive two-terminal electrical component that implements electrical resistance as a circuit element. Resistors act to reduce current flow, and, at the same time, act to lower voltage levels within circuits. Resistors may have fixed resistances or variable resistances, such as those found in thermistors, varistors, trimmers, photoresistors, humistors, piezoresistors and potentiometers. The current through a resistor is in direct proportion to the voltage across the resistor's terminals. This relationship is represented by Ohm's law. Whereas the current through the conductor in units of amperes, V is the potential difference measured across the conductor in units of volts, and R is the resistance of the conductor in units of ohms. The ratio of the voltage applied across a resistor's terminals to the intensity of current in the circuit is called its resistance, and this can be assumed to be a constant for ordinary resistors working within their ratings. Resistors are common elements of electrical networks and electronic circuits and are ubiquitous in electronic equipment. Practical resistors can be composed of various compounds and films, as well as resistance wires. Resistors are also implemented within integrated circuits, particularly analog devices, and can also be integrated into hybrid and printed circuits. The electrical functionality of a resistor is specified by its resistance. Common commercial resistors are manufactured over a range of more than 9 orders of magnitude. When specifying that resistance in an electronic design, the required precision of the resistance may require attention to the manufacturing tolerance of the chosen resistor, according to its specific application. The temperature coefficient of the resistance may also be of concern in some precision applications. Practical resistors are also specified as having a maximum power rating which must exceed the anticipated power dissipation of that resistor in a particular circuit. This is mainly of concern in power electronics applications. Resistors with higher power ratings are physically larger and may require heat sinks. In a high-voltage circuit, attention must sometimes be paid to the rated maximum working voltage of the resistor. While there is no minimum working voltage for a given resistor, failure to account for a resistor's maximum rating may cause the resistor to incinerate when current is run through it. Practical resistors have a series inductance and a small parallel capacitance. These specifications can be important in high-frequency applications. In a low-noise amplifier or preamp, the noise characteristics of a resistor may be an issue. The unwanted inductance, excess noise, and temperature coefficient are mainly dependent on the technology used in manufacturing the resistor. They are not normally specified individually for a particular family of resistors manufactured using a particular technology. A family of discrete resistors is also characterized according to its form factor, that is, the size of the device and the position of its leads, which is relevant in the practical manufacturing of circuits using them. Units. The ohm is the SI unit of electrical resistance, named after Georg Simon Ohm. An ohm is equivalent to a volt per ampere. Since resistors are specified and manufactured over a very large range of values, the derived units of milliohm, kiloohm, and megohm are also in common usage. The reciprocal of resistance R is called conductance G equals 1 per Rankine and is measured in Siemens, sometimes referred to as mho. Hence, Siemens is the reciprocal of an ohm. Although the concept of conductance is often used in circuit analysis, practical resistors are always specified in terms of their resistance rather than conductance. Electronic symbols and notation. The symbol used for a resistor in a circuit diagram varies from standard to standard and country to country. Two typical symbols are as follows. The notation to state a resistor's value in a circuit diagram varies too. The European notation avoids using a decimal separator, and replaces the decimal separator with the SI prefix symbol for the particular value. For example, 8K2 in a circuit diagram indicates a resistor value of 8.2, a key copyright. Additional zeros imply tighter tolerance, for example 15 mho. When the value can be expressed without the need for an SI prefix, an R is used instead of the decimal separator. For example, 1 or 2 indicates 1.2 AI copyright, and 18 or indicates 18 AI copyright. The use of a SI prefix symbol or the letter R circumvents the problem that decimal separators tend to disappear when photocopying a printed circuit diagram. Theory of operation. Ohm's law. The behavior of an ideal resistor is dictated by the relationship specified by Ohm's law. Ohm's law states that the voltage across a resistor is proportional to the current, where the constant of proportionality is the resistance. Equivalently, Ohm's law can be stated. This formulation states that the current is proportional to the voltage and inversely proportional to the resistance. This is directly used in practical computations. For example, if a 300 ohm resistor is attached across the terminals of a 12-volt battery, then a current of 12/300 equals 0.04 amperes flows through that resistor. Series and parallel resistors. In a series configuration, the current through all of the resistors is the same, but the voltage across each resistor will be in proportion to its resistance. The potential difference seen across the network is the sum of those voltages, thus the total resistance can be found as the sum of those resistances. As a special case, the resistance of n resistors connected in series, each of the same resistance R, is given by nR. Thus, if a 100 k ohm resistor and a 22 k ohm resistor are connected in series, their combined resistance will be 122 k ohm. They will function in a circuit as though they were a single resistor with a resistance value of 122 k ohm. 3 22 k ohm resistors will produce a resistance of 3x 22 k equals 66 k ohms. Resistors in a parallel configuration are each subject to the same potential difference, however the currents through them add. The conductances of the resistors then add to determine the conductance of the network. Thus the equivalent resistance of the network can be computed. So, for example, a 10 ohm resistor connected in parallel with a 5 ohm resistor and a 15 ohm resistor will produce the inverse of 15 plus 1 over 15 ohms of resistance, or 1/0.1 plus 0.2 plus 0.067, equals 2.725 ohms. The greater the number of resistors in parallel, the less overall resistance they will collectively generate, and the resistance will never be higher than that of the resistor with the lowest resistance in the group. The parallel equivalent resistance can be represented in equations by two vertical lines as a simplified notation. Occasionally two slashes are used instead of, in case the keyboard or font lacks the vertical line symbol. For the case of two resistors in parallel, this can be calculated using a resistor network that is a combination of parallel and series connections can be broken up into smaller parts that are either one or the other. For instance, however, some complex networks of resistors cannot be resolved in this manner, requiring more sophisticated circuit analysis. For instance, consider a cube, each edge of which has been replaced by a resistor. What then is the resistance that would be measured between two opposite vertices? In the case of 12 equivalent resistors, it can be shown that the corner-to-corner resistance is 5/6 of the individual resistance. More generally, the Y-I transform, or matrix methods can be used to solve such a problem. One practical application of these relationships is that a non-standard value of resistance can generally be synthesized by connecting a number of standard values in series or parallel. This can also be used to obtain a resistance with a higher power rating than that of the individual resistors used. In the special case of n identical resistors all connected in series or all connected in parallel, the power rating of the composite resistor is n times the power rating of the individual resistors. Power dissipation: at any instant of time, the power P consumed by a resistor of resistance R is calculated as, where V is the voltage across the resistor and I is the current flowing through it. The first form is a restatement of Joule's first law. Using Ohm's law, the two other forms can be derived. This power is converted into heat which must be dissipated by the resistor's package. The total amount of heat energy released over a period of time can be determined from the integral of the power over that period of time. Therefore one could write the average power dissipated over the particular time period as: if the time interval T1, T2 is chosen to be one complete cycle of a periodic waveform, then this result is equal to the long-term average power generated as heat which will be dissipated continuously. With a periodic waveform, then this average over complete cycles is conveniently given by where ohms and vrms are the root mean square values of the current and voltage. In any case, that heat generated in the resistor must be dissipated before its temperature rises excessively. Resistors are rated according to their maximum power dissipation. Most discrete resistors in solid-state electronic systems absorb much less than a watt of electrical power and require no attention to their power rating. Such resistors in their discrete form, including most of the packages detailed below, are typically rated as 1/10, 1/8, or 1/4 watt. Resistors required to dissipate substantial amounts of power, particularly used in power supplies, power conversion circuits, and power amplifiers, are generally referred to as power resistors. This designation is loosely applied to resistors with power ratings of 1 watt or greater. Power resistors are physically larger and may not use the preferred values, color codes, and external packages described below. If the average power dissipated by a resistor is more than its power rating, damage to the resistor may occur, permanently altering its resistance. This is distinct from the reversible change in resistance due to its temperature coefficient when it warms. Excessive power dissipation may raise the temperature of the resistor to a point where it can burn the circuit board or adjacent components, or even cause a fire. There are flame-proof resistors that fail before they overheat dangerously. Since poor air circulation, high altitude, or high operating temperatures may occur, resistors may be specified with higher rated dissipation than will be experienced in service. Some types and ratings of resistors may also have a maximum voltage rating. This may limit available power dissipation for higher resistance values. Fixed resistor lead arrangements. Through-hole components typically have leads leaving the body axially. Others have leads coming off their body radially instead of parallel to the resistor axis. Other components may be SMT, while high-power resistors may have one of their leads designed into the heat sink. Carbon composition. Carbon composition resistors consist of a solid cylindrical resistive element with embedded wire leads or metal end caps to which the lead wires are attached. The body of the resistor is protected with paint or plastic. Early 20th century carbon composition resistors had uninsulated bodies. The lead wires were wrapped around the ends of the resistance element rod and soldered. The completed resistor was painted for color coding of its value. The resistive element is made from a mixture of finely ground carbon and an insulating material. A resin holds the mixture together. The resistance is determined by the ratio of the fill material to the carbon. Higher concentrations of carbon a good conductor result in lower resistance. Carbon composition resistors were commonly used in the 1960s and earlier, but are not so popular for general use now as other types have better specifications, such as tolerance, voltage dependence, and stress. Moreover, if internal moisture content is significant, soldering heat will create a non-reversible change in resistance value. Carbon composition resistors have poor stability with time and were consequently factory sorted to, at best, only 5% tolerance. These resistors, however, if never subjected to overvoltage nor overheating, were remarkably reliable considering the component size. Carbon composition resistors are still available, but comparatively quite costly. Values ranged from fractions of an ohm to 22 megohms. Due to their high price, these resistors are no longer used in most applications. However, they are used in power supplies and welding controls. Carbon pile. A carbon pile resistor is made of a stack of carbon discs compressed between two metal contact plates. Adjusting the clamping pressure changes the resistance between the plates. These resistors are used when an adjustable load is required, for example in testing automotive batteries or radio transmitters. A carbon pile resistor can also be used as a speed control for small motors in household appliances with ratings up to a few hundred watts. A carbon pile resistor can be incorporated in automatic voltage regulators for generators, where the carbon pile controls the field current to maintain relatively constant voltage. The principle is also applied in the carbon microphone. Carbon film. A carbon film is deposited on an insulating substrate, and a helix is cut in it to create a long, narrow resistive path. Varying shapes, coupled with the resistivity of amorphous carbon, can provide a wide range of resistance values. Compared to carbon composition, they feature low noise, because of the precise distribution of the pure graphite without binding. Carbon film resistors feature a power rating range of 0.125 W to 5 W at 70 AA degrees Celsius. Resistances available range from 1 ohm to 10 megohm. The carbon film resistor has an operating temperature range of 55 AA degrees Celsius to 155 AA degrees Celsius. It has 200 to 600 volts maximum working voltage range. Special carbon film resistors are used in applications requiring high pulse stability. Printed carbon resistor. Carbon composition resistors can be printed directly onto printed circuit board substrates as part of the PCB manufacturing process. Whilst this technique is more common on hybrid PCB modules, it can also be used on standard fiberglass PCBs. Tolerances are typically quite large, and can be in the order of 30%. A typical application would be non-critical pull-up resistors. Thick and thin film. Thick film resistors became popular during the 1970s, and most SMD resistors today are of this type. The resistive element of thick films is 1,000 times thicker than thin films, but the principal difference is how the film is applied to the cylinder or the surface. Thin film resistors are made by sputtering the resistive material onto an insulating substrate. The film is then etched in a similar manner to the old process for making printed circuit boards. That is, the surface is coated with a photosensitive material, then covered by a pattern film, irradiated with ultraviolet light, and then the exposed photosensitive coating is developed, and underlying thin film is etched away. Thick film resistors are manufactured using screen and stencil printing processes. Because the time during which the sputtering is performed can be controlled, the thickness of the thin film can be accurately controlled. The type of material is also usually different, consisting of one or more ceramic conductors such as tantalum nitride, ruthenium oxide, AuO, 2, lead oxide, bismuth ruthenate, B2Ru, 2O, 7, nickel chromium, or bismuth iridate, B2A, 2O, 7. The resistance of both thin and thick film resistors after manufacture is not highly accurate. They are usually trimmed to an accurate value by abrasive or laser trimming. Thin film resistors are usually specified with tolerances of 0.1, 0.2, 0.5, or 1%, and with temperature coefficients of 5 to 25 ppmK. They also have much lower noise levels, on the level of 10^100 times less than thick film resistors. Thick film resistors may use the same conductive ceramics, but they are mixed with sintered glass and a carrier liquid so that the composite can be screen printed. This composite of glass and conductive ceramic material is then fused in an oven at about 850 degrees Celsius. Thick film resistors, when first manufactured, had tolerances of 5%, but standard tolerances have improved to 2% or 1% in the last few decades. Temperature coefficients of thick film resistors are high, typically A ± 200 or A ± 250 ppmK. A 40 Kelvin temperature change can change the resistance by 1%. Thin film resistors are usually far more expensive than thick film resistors. For example, SMD thin film resistors, with 0.5% tolerances, and with 25 ppmK temperature coefficients, when bought in full-size real quantities, are about twice the cost of 1%, 250 ppmK thick film resistors. Metal film. A common type of axial resistor today is referred to as a metal film resistor. Metal electrode leadless phase resistors often use the same technology, but are a cylindrically shaped resistor designed for surface mounting. Note that other types of resistors are also available in MELF packages. Metal film resistors are usually coated with nickel chromium, but might be coated with any of the cermet materials listed above for thin film resistors. Unlike thin film resistors, the material may be applied using different techniques than sputtering. Also, unlike thin film resistors, the resistance value is determined by cutting a helix through the coating rather than by etching. the result is a reasonable tolerance and a temperature coefficient that is generally between 50 and 100 ppm-K. Metal film resistors possess good noise characteristics and low non-linearity due to a low voltage coefficient. Also beneficial are the components' efficient tolerance, temperature coefficient and stability. Metal oxide film resistors are made of metal oxides such as tin oxide. This results in a higher operating temperature and greater stability reliability than metal film. They are used in applications with high endurance demands. Wire wound. Wire wound resistors are commonly made by winding a metal wire, usually nichrome, around a ceramic, plastic, or fiberglass core. The ends of the wire are soldered or welded to two caps or rings, attached to the ends of the core. The assembly is protected with a layer of paint, molded plastic, or an enamel coating baked at high temperature. These resistors are designed to withstand unusually high temperatures of up to +450 degrees Celsius. Wire leads in low-power wire wound resistors are usually between 0.6 and 0.8 ohm in diameter and tinned for ease of soldering. For higher power wire wound resistors, either a ceramic outer case or an aluminum outer case on top of an insulating layer is used. If the outer case is ceramic, such resistors are sometimes described as cement resistors, though they do not actually contain any traditional cement. The aluminum case types are designed to be attached to a heat sink to dissipate the heat. The rated power is dependent on being used with a suitable heat sink. For example, a 50W power-rated resistor will overheat at a fraction of the power dissipation if not used with a heat sink. Large wire wound resistors may be rated for 1000 watts or more. Because wire wound resistors are coils, they have more undesirable inductance than other types of resistor, although winding the wire in sections with alternately reversed direction can minimize inductance. Other techniques employ bifilar winding, or a flat thin former. For the most demanding circuits, resistors with Ayrton-Perry winding are used. Applications of wire wound resistors are similar to those of composition resistors with the exception of the high frequency. The high-frequency response of wire wound resistors is substantially worse than that of a composition resistor. Foil resistor. The primary resistance element of a foil resistor is a special alloy foil several micrometers thick. Since their introduction in the 1960s, foil resistors have had the best precision and stability of any resistor available. One of the important parameters influencing stability is the temperature coefficient of resistance. The TCR of foil resistors is extremely low, and has been further improved over the years. One range of ultra-precision foil resistors offers a TCR of 0.14 ppm a degree Celsius, tolerance A plus or minus 0.005%, long-term stability 25 ppm, 50 ppm, stability under load 0.03%, thermal EMF 0.1 AI 1/4 volt per degree Celsius, noise of 42 decibel, voltage coefficient 0.1 ppmv, inductance 0.08 AI 1/4 H, capacitance 0.5 pf. Ammeter shunts. An ammeter shunt is a special type of current-sensing resistor, having 4 terminals and a value in milliohms or even microohms. Current measuring instruments, by themselves, can usually accept only limited currents. To measure high currents, the current passes through the shunt, where the voltage drop is measured and interpreted as current. A typical shunt consists of 2 solid metal blocks, sometimes brass, mounted onto an insulating base. Between the blocks, and soldered or brazed to them, are 1 or more strips of low-temperature coefficient of resistance manganese alloy. Large bolts threaded into the blocks make the current connections, while much smaller screws provide voltage connections. Shunts are rated by full-scale current, and often have a voltage drop of 50 MV at rated current. Such meters are adapted to the shunt full current rating by using an appropriately marked dial face. No change need be made to the other parts of the meter. Grid resistor. In heavy-duty industrial high-current applications, a grid resistor is a large convection-cooled lattice of stamped metal alloy strips connected in rows between 2 electrodes. Such industrial-grade resistors can be as large as a refrigerator. Some designs can handle over 500 amperes of current, with a range of resistances extending lower than 0.04 ohms. They are used in applications such as dynamic braking and load banking for locomotives and trams, neutral grounding for industrial AC distribution, control loads for cranes and heavy equipment, load testing of generators and harmonic filtering for electric substations. The term grid resistor is sometimes used to describe a resistor of any type connected to the control grid of a vacuum tube. This is not a resistor technology. It is an electronic circuit topology. Special varieties: metal oxide varistor, cermet, phenolic, tantalum, water resistor, variable resistors, adjustable resistors. A resistor may have one or more fixed tapping points so that the resistance can be changed by moving the connecting wires to different terminals. Some wire-wound power resistors have a tapping point that can slide along the resistance element, allowing a larger or smaller part of the resistance to be used. Where continuous adjustment of the resistance value during operation of equipment is required, the sliding resistance tap can be connected to a knob accessible to an operator. Such a device is called a rheostat and has two terminals. Potentiometers. A common element in electronic devices is a three-terminal resistor with a continuously adjustable tapping point controlled by rotation of a shaft or knob. These variable resistors are known as potentiometers when all three terminals are present, since they act as a continuously adjustable voltage divider. A common example is a volume control for a radio receiver. Accurate, high-resolution panel-mounted potentiometers have resistance elements typically wire-wound on a helical mandrel, although some include a conductive plastic resistance coating over the wire to improve resolution. These typically offer 10 turns of their shafts to cover their full range. They are usually set with dials that include a simple turns counter and a graduated dial. Electronic analog computers used them in quantity for setting coefficients, and delayed sweep oscilloscopes of recent decades included one on their panels. Resistance decade boxes. A resistance decade box or resistor substitution box is a unit containing resistors of many values, with one or more mechanical switches which allow any one of various discrete resistances offered by the box to be dialed in. Usually the resistance is accurate to high precision, ranging from laboratory calibration grade accuracy of 20 parts per million, to field grade at 1%. Inexpensive boxes with lesser accuracy are also available. All types offer a convenient way of selecting and quickly changing a resistance in laboratory, experimental and development work without needing to attach resistors one by one, or even stock each value. The range of resistance provided, the maximum resolution, and the accuracy characterize the box. For example, one box offers resistances from 0 to 100 megohms, maximum resolution 0.1 ohm, accuracy 0.1%. Special devices. There are various devices whose resistance changes with various quantities. The resistance of NTC thermistors exhibit a strong negative temperature coefficient, making them useful for measuring temperatures. Since their resistance can be large until they are allowed to heat up due to the passage of current, they are also commonly used to prevent excessive current surges when equipment is powered on. Similarly, the resistance of the humistor varies with humidity. Metal oxide varistors drop to a very low resistance when a high voltage is applied, making them useful for protecting electronic equipment by absorbing dangerous voltage surges. One sort of photodetector, the photoresistor, has a resistance which varies with illumination. The strain gauge, invented by Edward E. Simmons and Arthur C. Rouge in 1938, is a type of resistor that changes value with applied strain. A single resistor may be used, or a pair, or four resistors connected in a Wheatstone bridge configuration. The strain resistor is bonded with adhesive to an object that will be subjected to mechanical strain. With the strain gauge and a filter, amplifier, and analog-digital converter, the strain on an object can be measured. A related but more recent invention uses a quantum tunneling composite to sense mechanical stress. It passes a current whose magnitude can vary by a factor of 10-12 in response to changes in applied pressure. Measurement. The value of a resistor can be measured with an ohmmeter, which may be one function of a multimeter. Usually, probes on the ends of test leads connect to the resistor. A simple ohm meter may apply a voltage from a battery across the unknown resistor, producing a current which drives a meter movement. The current, in accordance with Ohm's law, is inversely proportional to the sum of the internal resistance and the resistor being tested, resulting in an analog meter scale which is very nonlinear, calibrated from infinity to 0 ohms. A digital multimeter, using active electronics, may instead pass a specified current through the test resistance. The voltage generated across the test resistance in that case is linearly proportional to its resistance, which is measured and displayed. In either case, the low resistance ranges of the meter pass much more current through the test leads than do high resistance ranges, in order for the voltages present to be at reasonable levels but still measurable. Measuring low-value resistors, such as fractional ohm resistors, with acceptable accuracy requires 4 terminal connections. One pair of terminals applies a known, calibrated current to the resistor, while the other pair senses the voltage drop across the resistor. Some laboratory quality ohm meters, especially milliohm meters, and even some of the better digital multimeters sense using 4 input terminals for this purpose, which may be used with special test leads. Each of the 2 so-called Kelvin clips is a pair of jewels insulated from each other. One side of each clip applies the measuring current, while the other connections are only to sense the voltage drop. The resistance is again calculated using Ohm's law as the measured voltage divided by the applied current. Color code: the axial lead carbon resistors measured by the color codes marked on them. Information such as resistance value, tolerance, temperature coefficient measured by the color codes, and the amount of power identified by the size. The color bands of the carbon resistors can be 4, 5 or 6 bands, for all the first 2 bands represent first 2 digits to measure their value in ohms. The third band of a 4-banded resistor represents multiplier and the 4th band is tolerance. Whereas, the 5 and 6 color-banded resistors, the third band rather represents as third digit but the 4th and 5th bands represent as multiplier and tolerance respectively. Only the 6th band represents temperature coefficient in a 6-banded resistor. The measuring digits against color codes given in the following table. For example, the value of a 4-band carbon resistor having color bands red, 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 silver will have value 22 times 100 equals 2200 ohms with 10% tolerance. Standards: production resistors. Resistor characteristics are quantified and reported using various national standards. In the U.S., MIL STD-202 contains the relevant test methods to which other standards refer. There are various standards specifying properties of resistors for use in equipment: BS 1852, EIARS 279, MILPRF 26, MILPRF 39007, MILPRF 55342, MILPRF 914, MILR 11 standard cancelled, MILR 39017, MILPRF 32159. There are other United States military procurement MILR standards. Resistance standards. The primary standard for resistance, the mercury ohm, was initially defined in 1884 in as a column of mercury 106.3 cm long and 1 square millimeter in cross-section, at 0 degrees Celsius. Difficulties in precisely measuring the physical constants to replicate this standard result in variations of as much as 30 ppm. From 1900 the mercury ohm was replaced with a precision machine plate of manganine. Since 1990 the international resistance standard has been based on the quantized Hall effect discovered by Klaus von Klitzing, for which he won the Nobel Prize in Physics in 1985. Resistors of extremely high precision are manufactured for calibration and laboratory use. They may have 4 terminals, using one pair to carry an operating current and the other pair to measure the voltage drop. This eliminates errors caused by voltage drops across the lead resistances, because no charge flows through voltage-sensing leads. It is important in small-value resistors where lead resistance is significant or even comparable with respect to resistance standard value. Resistor marking. Most axial resistors use a pattern of colored stripes to indicate resistance. Surface mount resistors are marked numerically, if they are big enough to permit marking. more recent small sizes are impractical to mark. Cases are usually tan, brown, blue, or green, though other colors are occasionally found such as dark red or dark gray. Early 20th century resistors, essentially uninsulated, were dipped in paint to cover their entire body for color coding. A second color of paint was applied to one end of the element, and a color dot in the middle provided the third digit. The rule was body, tip, dot, providing two significant digits for value in the decimal multiplier, in that sequence. Default tolerance was A plus or minus 20%. Closer tolerance resistors had silver or gold-colored paint on the other end. Preferred values. Early resistors were made in more or less arbitrary round numbers. A series might have 100, 125, 150, 200, 300, etc. Resistors as manufactured are subject to a certain percentage tolerance, and it makes sense to manufacture values that correlate with the tolerance, so that the actual value of a resistor overlaps slightly with its neighbors. Wider spacing leaves gaps. Narrower spacing increases manufacturing and inventory costs to provide resistors that are more or less interchangeable. A logical scheme is to produce resistors in a range of values which increase in a geometrical progression, so that each value is greater than its predecessor by a fixed multiplier or percentage, chosen to match the tolerance of the range. For example, for a tolerance of A plus or minus 20%, it makes sense to have each resistor about 1.5 times its predecessor, covering a decade and 6 values. In practice, the factor used is 1.4678, giving values of 1.47, 2.15, 3.16, 4.64, 6.81, 10 for the €1 decade. These are rounded in practice to 1.5, 2.2, 3.3, 4.7, 6.8, 10. Followed by 15, 22, 33, €1 and preceded by €0 0.47, 0.68, 1. This scheme has been adopted as the E6 series of the IEC 60063 preferred number values. There are also E12, E24, E48, E96 and E192 series for components of progressively finer resolution, with 12, 24, 96, and 192 different values within each decade. The actual values used are in the IEC 60063 lists of preferred numbers. A resistor of 100 ohms A plus or minus 20% would be expected to have a value between 80 and 120 ohms. Its E6 neighbors are 68 and 150 ohms. A sensible spacing, E6 is used for A plus or minus 20% components. E12 for A plus or minus 10%. E24 for A plus or minus 5%. E48 for A plus or minus 2%, E96 for A plus or minus 1%. E192 for A plus or minus 0.5% or better. Resistors are manufactured in values from a few milliohms to about a gigaohm in IEC 60063 ranges appropriate for their tolerance. Manufacturers may sort resistors into tolerance classes based on measurement. Accordingly, a selection of 100 ohms resistors with a tolerance of A plus or minus 10%, may not lay just around 100 ohm as one would expect, but rather be in two groups either between 5 to 10% too high or 5 to 10% too low. Any resistors the factory measured as being less than 5% off, would have been marked and sold as resistors with only A plus or minus 5% tolerance or better. When designing a circuit, this may become a consideration. Earlier power wire wound resistors, such as brown vitreous enameled types, however, were made with a different system of preferred values, such as some of those mentioned in the first sentence of this section. 5-band axial resistors. 5-band identification is used for higher precision resistors, to specify a third significant digit. The first 3 bands represent the significant digits, the fourth is the multiplier, and the fifth is the tolerance. 5-band resistors with a gold or silver fourth band are sometimes encountered, generally on older or specialized resistors. The fourth band is the tolerance and the fifth the temperature coefficient. SMT resistors. Surface-mounted resistors are printed with numerical values in a code related to that used on axial resistors. Standard tolerance surface mount technology resistors are marked with a 3-digit code, in which the first 2 digits are the first 2 significant digits of the value and the third digit is the power of 10. For example, resistances less than 100 ohms are written 100, 220, 470. The final 0 represents 10 to the power 0, which is 1. For example, sometimes these values are marked as 10 or 22 to prevent a mistake. Resistances less than 10 ohms have R to indicate the position of the decimal point. For example, precision resistors are marked with a 4-digit code, in which the first 3 digits are the significant figures and the fourth is the power of 10. For example, 000 and 0000 sometimes appear as values on surface mount 0-ohm links, since these have 0 resistance. More recent surface mount resistors are too small, physically, to permit practical markings to be applied. Industrial type designation, format, 2 letters space, resistance value no space, tolerance code, numerical a 1 digit. Electrical and thermal noise. In amplifying faint signals, it is often necessary to minimize electronic noise, particularly in the first stage of amplification. As a dissipative element, even an ideal resistor will naturally produce a randomly fluctuating voltage or noise across its terminals. This Johnson-Nyquist noise is a fundamental noise source which depends only upon the temperature and resistance of the resistor, and is predicted by the fluctuation-dissipation theorem. Using a larger resistor produces a larger voltage noise, whereas with a smaller value of resistance there will be more current noise, assuming a given temperature. The thermal noise of a practical resistor may also be somewhat larger than the theoretical prediction, and that increase is typically frequency dependent. However, the excess noise of a practical resistor is an additional source of noise observed only when a charge flows through it. This is specified in unit of I1/4 decade a I1/4 V of noise per volt applied across the resistor per decade of frequency. The I1/4 decade value is frequently given in decibels so that a resistor with a noise index of 0 decibel will exhibit 1 I1/4 V of excess noise for each volt across the resistor in each frequency decade. Excess noise is thus an example of 1 per Fahrenheit noise. Thick film and carbon composition resistors generate more excess noise than other types at low frequencies. Wire wound and thin film resistors, though much more expensive, are often utilized for their better noise characteristics. Carbon composition resistors can exhibit a noise index of 0 decibels while bulk metal foil resistors may have a noise index of 40 decibels, usually making the excess noise of metal foil resistors insignificant. Thin film surface mount resistors typically have lower noise and better thermal stability than thick film surface mount resistors. Excess noise is also size dependent. In general, excess noise is reduced as the physical size of a resistor is increased, as the independently fluctuating resistances of smaller components will tend to average out. While not an example of noise per se, a resistor may act as a thermocouple, producing a small DC voltage differential across it due to the thermoelectric effect if its ends are at somewhat different temperatures. This induced DC voltage can degrade the precision of instrumentation amplifiers in particular. Such voltages appear in the junctions of the resistor leads with the circuit board and with the resistor body. Common metal film resistors show such an effect at a magnitude of about 20 microvolt a degree Celsius. Some carbon composition resistors can exhibit thermoelectric offsets as high as 400 microvolt a degree Celsius, whereas specially constructed resistors can reduce this number to 0.05 microvolt a degree Celsius. In applications where the thermoelectric effect may become important, care has to be taken to mount the resistors horizontally to avoid temperature gradients and to mind the airflow over the board. Failure modes. The failure rate of resistors in a properly designed circuit is low compared to other electronic components such as semiconductors and electrolytic capacitors. Damage to resistors most often occurs due to overheating when the average power delivered to it greatly exceeds its ability to dissipate heat. This may be due to a fault external to the circuit, but is frequently caused by the failure of another component in the circuit connected to the resistor. Operating a resistor too close to its power rating can limit the resistor's lifespan or cause a change in its resistance over time which may or may not be noticeable. A safe design generally uses overrated resistors in power applications to avoid this danger. Low-power thin-film resistors can be damaged by long-term high-voltage stress, even below maximum specified voltage and below maximum power rating. This is often the case for the startup resistors feeding the SMPS integrated circuit. When overheated, carbon film resistors may decrease or increase in resistance. Carbon film and composition resistors can fail if running close to their maximum dissipation. This is also possible but less likely with metal film and wire wound resistors. There can also be failure of resistors due to mechanical stress and adverse environmental factors including humidity. If not enclosed, wire wound resistors can corrode. Surface mount resistors have been known to fail due to the ingress of sulfur into the internal makeup of the resistor. This sulfur chemically reacts with a silver layer to produce non-conductive silver sulfide. The resistor's impedance goes to infinity. Sulfur-resistant and anti-corrosive resistors are sold into automotive, industrial, and military applications. ASTM B809 is an industry standard that tests a part's susceptibility to sulfur. An alternative failure mode can be encountered where large-value resistors are used. Resistors are not only specified with a maximum power dissipation, but also for a maximum voltage drop. Exceeding this voltage will cause the resistor to degrade, slowly reducing in resistance. The voltage dropped across large-value resistors can be exceeded before the power dissipation reaches its limiting value. Since the maximum voltage specified for commonly encountered resistors is a few hundred volts, this is a problem only in applications where these voltages are encountered. Variable resistors can also degrade in a different manner, typically involving poor contact between the wiper and the body of the resistance. This may be due to dirt or corrosion and is typically perceived as crackling as the contact resistance fluctuates. This is especially noticed as the device is adjusted. This is similar to crackling caused by poor contact in switches, and like switches, potentiometers are to some extent self-cleaning. Running the wiper across the resistance may improve the contact. Potentiometers which are seldom adjusted, especially in dirty or harsh environments, are most likely to develop this problem. When self-cleaning of the contact is insufficient, improvement can usually be obtained through the use of contact cleaner spray. The crackling noise associated with turning the shaft of a dirty potentiometer in an audio circuit is greatly accentuated when an undesired DC voltage is present, often indicating the failure of a DC blocking capacitor in the circuit. See also: circuit design, dummy load, electrical impedance, iron-hydrogen resistor, shot noise, trimmer, references. External links: 4-terminal resistors How ultra-precise resistors work, Beginner's Guide to Potentiometers, including description of different tapers, color-coded resistance calculator, archived with Wayback Machine, resistor types Does it matter? Standard resistors and capacitor values that industry manufactures, ask the applications engineer difference between types of resistors and their uses, thick film resistors and heaters.